On the 27th of December 2004, one day after a wave in the Indian Ocean had taken more than 200,000 lives, a second wave reached the Earth. This one did not touch the water. It came from the far side of the galaxy, from a single point in the constellation Sagittarius, 50,000 light years away. It was a wave of pure energy, and it had been travelling toward us since before our species learned to use fire. For 0.2 of 1 second, it was the brightest thing in our sky after the sun. It outshone the full moon. It pressed against the upper edge of our atmosphere and pushed it inward, the way a hand pushes against a sheet of stretched rubber. Spacecraft built to stare at the sun were blinded by it. Detectors designed to catch the death of distant stars were overwhelmed, saturated, unable to measure something so bright. And the thing that made it was not a star in any sense you would recognize. It was the corpse of one, a ball of dead matter the size of a city, spinning alone in the dark, 50,000 light years from anyone who would ever feel what it had done. It is the most magnetic object in the known universe. It is, by several honest measures, the most dangerous. And the strangest thing about it is not how it can kill, it is what it can build. Let us begin. The object has a name. It is called a magnetar, and to understand what one is, you first have to understand how a star dies. When a massive star, many times heavier than our Sun, runs out of fuel, it can no longer hold itself up. For its entire life, the star has been balanced between two forces. Gravity pulls everything inward. The heat of nuclear fusion in its core pushes everything outward. The two are matched, and the star stays stable, sometimes for millions of years. But fusion needs fuel. When the fuel runs out, the outward push stops. Gravity does not. In less than a single second, the core of the star falls in on itself. What happens next is hard to picture, so hold on to one number. The collapsing core takes the mass of something larger than our Sun and crushes it into a ball about 20 kilometers across. That is the size of a city. A single spoonful of the matter inside it would weigh about as much as a mountain. The outer layers of the star, meanwhile, rebound off the crushed core and are thrown outward in a supernova. For a few weeks, that one dying star can outshine an entire galaxy of hundreds of billions of others. And when the light finally fades, what is left behind in the wreckage is the core. A neutron star, the densest object the universe knows how to make without folding it away into a black hole. Most neutron stars are strange enough on their own, but a small number of them are born with something extra. As the core collapses, it spins faster, the same way a figure skater spins faster when she pulls her arms in toward her body. And in the first 10 seconds of the new star's life, while its inside is still molten and churning, that spin can drive a kind of engine. The churning fluid behaves like the dynamos that generate the magnetic fields of planets and ordinary stars, except here it is packed into something city-sized and almost unimaginably dense. The field it produces does not fade away, it locks in, and it is unlike anything else we have ever found. Here is what that field is. The Earth has a magnetic field. It is the thing that turns a compass needle, and it measures about 1/2 of 1 Gauss. A refrigerator magnet is around 100 Gauss. A hospital MRI machine, one of the strongest magnetic fields most people will ever stand inside, reaches a few tens of thousands. A large sunspot, a magnetic storm on the surface of our own Sun, can reach 10,000. A magnetar's field can reach 1,000 trillion Gauss. Write that out, and it is a 1 followed by 15 zeros. The magnetar that lit our sky in 2004, catalogued as SGR 1806-20, has been estimated by NASA's Goddard Space Flight Center at around 800 trillion Gauss, the strongest magnetic field ever measured anywhere in nature. It is roughly 1,000 trillion times stronger than the field you are sitting in right now. The two physicists who first proposed that such objects could exist, Robert Duncan of the University of Texas at Austin and Christopher Thompson, working together in 1992, gave them their name by fusing two words: magnetic, star, magnetar. For 6 years it was only a theory. Then, in 1998, the astrophysicist Krista Kuveliotu at NASA's Marshall Space Flight Center turned two X-ray satellites toward SGR 1806-20 and watched it spin. It turned once every 7.5 seconds, and it was slowing down by 0.003 of a second each year. There was only one thing in physics that could break a spinning star that hard: a magnetic field exactly as monstrous as the theory had predicted. The idea became an object. The object was real, and it was heating its own surface to 18 million degrees Fahrenheit, simply by being what it was. It is hard to feel a number as large as 1,000 trillion, so consider what such a field would do to you. A magnetic field is not a gentle thing when it grows this strong. It pulls on the very structure of matter, on the electrons inside every atom of every object near it. Under a magnetar's field, atoms are no longer round. They are squeezed into thin needles, stretched out along the lines of the field. A hydrogen atom near a magnetar is compressed to roughly 200 times narrower than it is here on Earth. Matter itself stops behaving the way matter is supposed to behave. Even the empty space around the star is changed. According to the physics of quantum electrodynamics, the magnetized vacuum begins to bend light like a prism, polarizing it the way a pair of sunglasses polarizes the glare off a road. Your body is held together by the bonds between its molecules, and those bonds are, at their root, electromagnetic. A magnetar would not need to touch you to take you apart. From thousands of kilometers away, its field would distort and break the bonds holding your body together. You would not be crushed, and you would not be burned. You would simply come undone, atom by atom, in a field too strong for chemistry itself to survive. The astrophysicist Oliver Roberts of the University's Space Research Association once put the scale of it in terms anyone can hold in their hand. If you placed a magnetar halfway between the Earth and the Moon, he said, it would strip the magnetic strip from every credit card on the planet and wipe every hard drive from nearly 200,000 kilometers away. Not the heat, not the radiation, the magnetism alone, reaching across that gulf to the Earth and quietly erasing it. There is a mercy in all of this, and the mercy is distance. Right now, as you hear this, there are only about 30 magnetars known in our entire galaxy. The Milky Way holds hundreds of billions of stars, and only a few dozen of these. They are rare, they are short-lived, and every single one we have found is very far away. The nearest are still thousands of light years from us, far enough that the field which would unmake a human body up close is, by the time it reaches the Earth, almost nothing at all. Almost. Because in 2004, one of them reminded us that distance is not the same thing as safety. SGR 1806-20 is what astronomers call a soft gamma repeater, a magnetar that flares up at random and throws off bursts of gamma rays. It had done this many times. But on the 27th of December, it did something it had done only twice before in all the years we had been watching the sky. It released a giant flare. The previous two, recorded in 1979 and 1998, had been violent enough. This one was roughly 100 times more powerful than either. When it arrived, it had already crossed 50,000 light years, the entire width of our galaxy, and it still reached down and pushed on the top of our air. Brian Gainsler, then at the Harvard-Smithsonian Center for Astrophysics, studied the fading radio glow the flare left behind. Had the same eruption happened within 10 light years of the Earth, he concluded, it would have severely damaged our atmosphere. There are no magnetars that close to us, but the sentence is worth sitting with. A dead remnant the size of a city on the far side of the galaxy released enough energy in 0.2 of 1 second to threaten a planet 10 light years away. In that 1/5 of a second, it gave off more energy than our sun radiates in 250,000 years. And this is the part that should stop you. The energy of that flare did not come from fusion, the way a living star's light does. The magnetar was already dead. It had no fuel left to burn. The light that crossed the whole galaxy and struck our sky came from the magnetic field alone, from something bending and straining and finally breaking on the surface of a corpse. A dead star should be quiet, This one was not. And the question of how a dead thing can release 250,000 years of sunlight in the space of a single breath is where this story goes next. The easy answers fail first. They always do. The easiest answer to the question we ended on is also the most comforting one, because it says the question itself is wrong. A dead star cannot erupt, it tells us, because a dead star does nothing at all. When a star dies, the story is supposed to be over. The core cools, the light fades, the remnant settles into the dark and waits, for billions of years, to cool a little further. That is what a corpse does. It does not reach across 50,000 light years and press on the atmosphere of a living world. And yet, on the 27th of December, 2004, one of them did exactly that. So the easy answer fails, and we are left with the harder one. The magnetar was dead, but it was not empty. It still had fuel, and the fuel was the field itself. A magnetar's magnetic field carries an almost unthinkable amount of energy, wound into the body of the star like the tension in a coiled spring. In a living star, the energy comes from fusion burning in the core. In a magnetar, the energy is the magnetism, and nothing more. There is no fire left. There is only the field, holding more power in its invisible lines than the sun pours out in 100,000 years of burning. We tend to think of magnetism as something faint and harmless, the small tug that holds a note to a refrigerator door. We forget that it is one of the fundamental forces of nature, and that when you concentrate enough of it into a small enough space, it stops being faint and starts being the most violent thing for light years in every direction. A magnetar is what that looks like, and magnetism this strong does not sit quietly. Beneath the surface, the magnetar is not solid. Its interior is a churning fluid of neutrons and charged particles, very nearly a perfect conductor of electricity, and it is always moving. As it moves, it drags the magnetic field along with it, winding it tighter and tighter, the way you might twist a rubber band between two fingers until it knots and strains against itself. But the surface of the star is not fluid. The surface is a crust of crystalline iron, perhaps a single kilometer thick, and it may be the most rigid material that exists anywhere in the universe. So the field winds tighter underneath. The rigid crust holds it down. The stress builds and builds and builds until the crust can no longer hold. When it fails, the event has a name: a starquake. Picture it: the most rigid material in the universe, cracking and shifting under a force strong enough to bend a dead star out of its shape. Christopher Thompson and Robert Duncan, the same two physicists who gave these objects their name, proposed in 1995 that this is what powers the flares. The crust reaches its breaking point. The trapped magnetic field, suddenly freed, snaps into a new shape and hurls a fireball of energy off the surface of the star. On an object so dense and so strained that a shift of a single centimetre of crust can release a catastrophe, the giant flare of 2004 was very likely a starquake on a global scale, a failure of the entire surface of the star, all at once. But here too, the easy picture fails. We say the word crack because we know what cracks are. We have felt earthquakes. We imagine the crust splitting open like dry ground in a drought. The truth is stranger than that. The same colossal field that breaks the crust also holds the broken pieces together, pinning them in place with a magnetic tension that an ordinary fracture could never overcome. A simple crack, the kind that shakes the earth, would be smothered before it could ever release its energy. So the flare cannot be only a break in the crust. It must also be the magnetic field itself, catastrophically rearranging, untwisting and reconnecting in a fraction of a second, the way the sun's field reconnects to make a solar flare, but on a scale no star still burning could ever reach. Whether the quake comes first and triggers the field, or the field comes first and triggers the quake, we do not know. We know only this: when a magnetar lets go, it lets go with the force of 250,000 years of sunlight, in less time than it takes to blink. Which leaves the deeper question: not why a magnetar flares, But why a magnetar exists at all? The galaxy holds hundreds of billions of stars. The overwhelming majority of those that die as neutron stars become ordinary ones, with fields 100 or 1,000 times weaker than a magnetar's. Only a tiny handful, around 30 that we have ever found, cross the line into something monstrous. Something sets them apart, and we are not certain what it is. The leading idea reaches back to those first 10 seconds of the new star's life, when the core is freshly collapsed, still molten and spinning. If it spins fast enough, the churning interior behaves like a dynamo, the same kind of process that generates the magnetic field of the Earth itself. And it can amplify the field 1,000-fold and lock it in place forever. But this demands that the newborn star be spinning extraordinarily fast at the very moment of its birth, and not every dying star does. So perhaps a magnetar is simply the rare one that was already spinning hard when it died. Or perhaps its field was inherited, a fossil left behind by a parent star that was already unusually magnetic. Or perhaps the answer is stranger still. In 2023, the astronomer Thomas Schoenaar, then at the University of Amsterdam, found a star that may be the answer caught in the act. It is called HD 45166, and it is the most magnetic massive star ever discovered. By the standards of ordinary stars, its field is enormous, and the calculations suggest that when it finally dies and collapses, the collapse will concentrate that field into something near 100 trillion scenes, a magnetar in waiting. The strange part is how the star itself seems to have formed. The evidence points to a merger, two smaller stars that spiraled together and became one, and in the violence of that union, built a magnetic field that nothing born alone could match. The strongest magnets in the universe, it seems, may be forged by collision. Brian Gainsler at Harvard had reached a related conclusion years before, in 2005, when he traced the most powerful of these objects back to the most massive stars. The biggest stars, when they die, make the strongest magnets. For a long time, all of this remained inference. We saw magnetars only after they already existed, already dead, already spinning in the dark. We had never once watched one being born. That changed only this year. In March of 2026, a team led by the astrophysicist Joseph Farah of Las Cumbres Observatory and the University of California, Santa Barbara, published in the journal Nature what may be the first sighting of a magnetar coming into existence. They had been watching a superluminous supernova, an explosion 10 to 100 times brighter than an ordinary one, more than 1 billion light-years away. As it faded, its light did something no supernova had ever been seen to do. It did not dim smoothly. It flickered, brightening and dimming in a series of 4 pulses that arrived faster and faster, like the chirp of a bird or the rising note of 2 black holes spiraling toward each other. The only thing that could explain the rhythm was a newborn magnetar at the center of the blast, wobbling in a way that only the warping of space-time by a spinning mass, an effect predicted by Einstein's general relativity, could produce. For the first time, we had not found a magnetar, we had watched one being made, inside the brightest kind of death a star can suffer. And the ones already out there are not silent. They are still speaking to us, in a language we are only beginning to learn to read. In April of 2020, a magnetar in our own galaxy, catalogued as SGR 1935 plus 2154 and lying some 30,000 light-years away, sent out a single burst of radio waves lasting only a few thousandths of a second. It was caught by 2 instruments at the same moment, the CHIME telescope in Canada and a small array in California, in work led by Paul Schultz of the University of Toronto and Christopher Bochenek of the California Institute of Technology. The burst was extraordinary. It was so bright and so brief that it matched a phenomenon astronomers had been chasing for more than a decade: fast radio bursts, intense flashes of radio energy that, until that night, had only ever been seen erupting from galaxies far beyond our own, with no known source. For the first time, one of those bursts had come from an object we could point to and name inside our own galaxy: a magnetar. one of the deepest mysteries in modern astronomy, traced in an instant back to the corpse of a star. So we know far more than we once did, and we know how little that still is. We do not fully understand why a few dying stars become magnetars, and almost none of the rest do. We do not know exactly what breaks first when they flare, the crust or the field. We do not know how many of the radio bursts washing over the Earth each day are magnetars calling out from galaxies we will never reach. What we do know is that these objects are not the quiet endings they appear to be. They are engines. They run on the most powerful force a dead star can hold, and every so often, without warning, that engine fires. When it fired in 2004, it did something almost no one noticed at the time. About 10 minutes after the giant flare, after the blinding spike had passed and the saturated instruments had recovered their sight, there came a second signal, a faint, slow glow from the same dead star, far weaker than the flare itself and far harder to explain. For 20 years, no one could say what it was. The answer, when it finally arrived, would have nothing to do with destruction. It would be about creation. And it is where this story arrives at its final and strangest stage. For 20 years, the second signal sat in the data, waiting. When the giant flare from SGR 1806-20 reached the Earth on the 27th of December 2004, the brightest part of it was over in a fifth of a second. But the instruments kept watching, and about 10 minutes after the initial blast, the gamma-ray telescope aboard NASA's Swift Observatory caught something else, coming from the same point in the sky. A second signal, far fainter than the flare, far slower. A soft glow of gamma rays that rose and faded over the minutes that followed, with no obvious reason to exist. No one could explain it. It did not match the flare. It did not match anything. So it was noted and set aside, and for 2 decades it remained one of those small, unsolved things that gather at the edges of a science, too faint to chase, too strange to forget. The flare had been the headline. The afterglow was a footnote, and the footnote held the answer to a question that had nothing to do with how a magnetar destroys, and everything to do with what it leaves behind. The answer began not with the old data, but with a calculation. In December of 2024, the astrophysicist Brian Metzger of Columbia University and the Flatiron Institute in New York was working with his colleagues on a question that had been quietly nagging at the field for years. We know that gold and platinum and uranium and the other heaviest elements in the universe are not made the way the common ones are. They are not forged in the slow burning of a star's core. They demand something far more violent. For a long time, astronomers believed they knew the recipe well enough. Metzger's group wanted to know whether a magnetar's giant flare could be one of the ovens. So they built a model of what should happen when a flare rips material off the star's crust and flings it into space. And the model made a prediction. If a giant flare truly did forge heavy elements, there should be a specific signal afterward, a delayed glow of gamma rays, rising and fading in the minutes after the blast, as the freshly made elements settled into being. When they shared the prediction, a colleague pointed them toward the 2004 flare, toward the footnote, the second signal. It matched. Anirudh Patel, a doctoral student at Columbia who worked with Metzger and led the new study, compared the model against the 20-year-old data, and the shape of the forgotten signal was almost exactly what the theory had drawn. As Patel later said, none of them, when they built the model, had known the signal was already sitting in the data, recorded 2 decades earlier and waiting. The team published their findings in the Astrophysical Journal Letters on the 29th of April 2025. Alongside Patel and Metzger were Jakub Cehula of Charles University in Prague, Eric Burns of Louisiana State University, and Jared Goldberg of the Flatiron Institute. They had not set out to solve a 20-year-old mystery. They had set out to ask where gold comes from. The 2 questions turned out to be the same question, because that faint second glow, the one no one could explain, was the light of new elements being born. To understand how, you have to understand why the heavy elements are so hard to make. Everything up to iron, a star can build by ordinary fusion, pressing lighter nuclei together in its core. But beyond iron, fusion stops paying its way. To build something heavier, gold, with its 79 protons, or uranium, with its 92, you cannot simply fuse. You have to flood an atomic nucleus with neutrons, faster than the nucleus can fall apart, packing them in until the atom is forced to become something heavier. Astronomers call it the rapid process, the R process, and the word rapid is the whole problem. A free neutron, left on its own, survives only about 15 minutes before it decays away. So the R process can happen only in a place with a staggering supply of free neutrons, and it has to happen fast. There are not many places like that in the universe, but a magnetar's crust is one of them. It is made of matter so dense and so neutron-rich that it barely counts as ordinary material at all. And when a giant flare tears a piece of that crust loose and hurls it into space, it scatters, for a few brief moments, exactly the conditions the R process needs. Free neutrons, in overwhelming numbers, slamming into nuclei faster than those nuclei can decay. In that instant, gold is made. Platinum is made. Uranium is made. Not by a living star, but by the violence of a dead one tearing off a piece of itself. The newly forged elements are born radiated, radioactive and unstable, and as they settle and decay into their final stable forms, they give off a glow of gamma rays rising and fading over minutes. The exact glow that struck the Earth 10 minutes after the flare in 2004 and then waited 20 years for someone to recognize it for what it was. It was not the afterglow of destruction. It was the light of creation, the receipt for a batch of gold. And the batch was not small. When the team ran the numbers on that single flare, the figure was difficult to hold in the mind. In its eruption, SGR 1806-20 had forged roughly 2 million billion kilograms of heavy elements, about the mass of the planet Mars, an entire world's worth of gold and platinum and rarer things made in an event that lasted, at its peak, 1/5 of 1 second. From this, the researchers estimated that magnetar flares like it may have produced somewhere between 1 and 10% of all the heavy elements in our galaxy. Some fraction of every piece of gold ever held in a human hand traces back to a flash like this one. Gold is rare on the Earth for the same reason it is precious. There is no process on our planet that makes it. Every atom of it had to be delivered, already formed, from somewhere violent and unspeakably far away. And when you sit with that, the long human obsession with the metal takes on a stranger colour. We have spent much of our history mining it, hoarding it, fighting and dying over it, a substance that cannot be made on Earth at all, that can only be born in the most catastrophic events the universe is capable of, and then carried here across the dark, long before there was anyone alive to want it. But here the story asks for honesty, because the easy version of it would be a lie. A magnetar flare is not the only forge, and it is almost certainly not the largest. To see where it fits, it helps to know how long the question has been open. For most of the 20th century, astronomers believed the heavy elements were built in supernovae, the explosions of dying stars. The idea was laid out in a famous paper in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler and Fred Hoyle. Work so foundational that much of what we understand about how stars forge the elements still rests upon it. And it was largely right. Stars do make most of the elements, but the very heaviest, the gold and the platinum and the uranium, never quite fit. The numbers did not add up. Ordinary supernovae did not seem to make enough of them, and for decades the true source remained one of the great open questions of the field. The first clear answer came in 2017. That year, astronomers detected 2 neutron stars colliding, not by their light at first, but by the ripple the collision sent through space-time itself, a gravitational wave. They turned their telescopes toward the source and watched the glow of freshly forged heavy elements rising from the wreckage. It was the first time anyone had directly witnessed gold being made anywhere in the universe. For years afterward, the merger of neutron stars stood as the leading answer to the question of where the heaviest things come from. When two of these dead stars spiral together and merge, they fling out a far greater quantity of heavy elements than any single flare. By one estimate, a single merger produces around 10,000 times more R-process material than one magnetar flare does. The mergers are rarer, but each one is vastly richer. So the magnetar has not overturned the picture, it has joined it. Gold, it now appears, is made in more than one kind of disaster, and we do not yet know the exact share that belongs to each. Brian Metzger has been careful to say so. We cannot rule out, he has noted, that there is a third source, or a fourth, that we simply have not found yet. To settle it, astronomers will have to catch a giant flare as it happens and read the elements directly in its light. A new gamma-ray telescope built partly for that purpose, named COSY, is expected to launch in 2027, with Eric Burns and his colleagues at Louisiana State University among those preparing to use it. The next time a magnetar tears itself open, we may be able to see, almost as it happens, exactly which elements it has forged. What the magnetar adds is something the mergers cannot: time. Two neutron stars take a very long while to find each other and fall together, long after a galaxy has grown old enough to make them in the first place. But a magnetar can flare almost as soon as it is born, in the very first generations of stars, when the universe was still young. Eric Burns of Louisiana State University put the implication plainly. Giant flares should have happened just after the first stars died, which means a magnetar may have made the very first gold the universe ever held, long before any pair of neutron stars had a chance to collide. The deadliest object in the cosmos may also have been the first thing in it to mint anything precious at all. If that is true, then for a long early stretch of cosmic history, every speck of gold in existence had been forged by a magnetar. The mergers came later, the flares came first, and all of it ends up somewhere. The gold forged in a flare does not stay beside the dead star that made it. It is flung outward into the cold gas that drifts between the stars, and it switches, and over millions of years it becomes part of the great clouds from which new stars and new worlds condense. About 4.5 billion years ago, one such cloud collapsed to form our Sun, and the planets around it, and the Earth. Whatever gold had been woven into that cloud was woven into the Earth as it formed. Most of it sank with the iron into the molten core, far out of reach. The gold we can actually touch, the gold in every vault and every ring, is thought to be only a thin trace near the surface, much of it delivered later still by asteroids that struck the young Earth long after it had formed. And even that was made in the same kind of distant violence. Every wedding ring, every gold tooth. The faint traces of gold and rarer metals in the phone you may be holding right now, and in the device carrying this voice to you. None of it was made on the Earth. All of it was made before the Earth existed, in the death throes of stars, and some unknown fraction of it was made in exactly the kind of event we have been describing. A magnetar tearing off a piece of its own crust, in a flash that would have killed anything close enough to watch it happen. This is the thing worth sitting with at the end. We began with the most dangerous object in the known universe, an object whose magnetic field would pull a human body apart, atom by atom, from thousands of kilometers away. An object that, from the far side of the galaxy, reached across 50,000 light-years and pressed on the air of our planet. Everything about a magnetar is built to destroy, and yet the same force, the same flare, the same act of a dead star ripping itself open, is one of the few events in all of creation capable of making the most prized substance human beings have ever known. The thing that would unmake you is the same thing that made the gold on your hand. In a magnetar, destruction and creation are not opposites. They are the same instant, seen from two sides. It is worth remembering the next time the universe seems only cold or only cruel. The same conditions that make a place lethal are sometimes the only ones that can make a place generative. The forces that tore the early cosmos apart are the same forces that filled it with everything we are built from. We are not separate from that violence. We are its sediment. The calcium in your bones, the iron in your blood, the gold you might be wearing right now, were all made in deaths like this one, scattered across the dark and slowly gathered into something that could one day wake up and wonder where it came from. The magnetars are still out there, about 30 of them that we know of, scattered through the galaxy, every one of them far away. They are turning slowly in the dark, exactly as they have for thousands of years, their fields winding tighter beneath their rigid surfaces, the stress building, quietly, toward the next break. Right now, as you hear this, somewhere in the Milky Way, a dead star is straining against itself. One day its crust will fail. For a fifth of a second it will be brighter than anything near it, and it will tear a piece of itself loose. And in that piece, gold will be born. The flash will travel through the dark for tens of thousands of years before it reaches anyone at all. By the time it does, the star will have long since gone quiet again. It will look, to whoever finally sees it, like an ending. A dead thing, briefly violent, falling still. It will be the opposite. It will be a forge, lighting once, in the dark, and making something that will outlast it.